So the uniform distribution does a good job of describing populations where any outcome within the range of possible outcomes is equally likely. If you've got a school where kids are between the ages of 5 and 15, then any age in between is equally likely. If you pick a kid at random from that population, any age between that 5 and 15 is equally likely to occur. If you show up at a bus stop where the bus runs every 10 minutes, every wait time for you between 0 and 10 minutes is equally likely. Now, not everything in the world is like that. It's good for describing the things that are, but there are other things where shorter times are more likely to occur than longer times. The example I like to use is wait time at McDonald's. When I pull into McDonald's, most of the time, there's not anybody in front of me at the counter. But there's that 1 in a million time when you pull in after the school bus full of a soccer team, and it takes them 25 minutes to eventually take your order. So we need a distribution here that has the shorter things or the younger things more likely than the older things or the longer things. Another example is the lifespan of fruit flies. They don't tend to live very long, so most of them have a fairly short lifespan, but some of them, a smaller and smaller number, have longer and longer lifespans. I've heard this always explained as describing the lifespan of a light bulb. And I don't think people would still be buying light bulbs if the majority of them burned out after such a short time. So I don't think that's accurate. This is called the exponential distribution, and in the next video we're going to look at how exponents come into it. We're not going to talk about that this time. But it describes a situation where the vast majority of the population is fairly low, be it lifespan or wait time or whatever we're talking about. And we do have some longer lifespans or wait times, but fewer and fewer and fewer of them the longer we're talking about. Okay, so the majority, short-lived, but then there's some up here in this tail. Very asymmetric. This is the only asymmetric distribution we're looking at in this part of the course. Good news here is the mean of the population has to be given. The mean of the distribution has to be given. We can't figure it out without it being told to us. So you don't have to learn to find the mean. You just have to know what it is. It'll be given anytime we're dealing with exponential distribution. The standard deviation, we're lucky there too. That happens to be equal to the mean. Whatever the mean is, that's the standard deviation. Couldn't be simpler than that. And the reason, of course, that we want the mean and the standard deviation is we want to be able to find that range of likely outcomes, our ROLO. And we always find that by taking the mean minus 2 standard deviations and the mean plus 2 standard deviations. So in this case, the mean and the standard deviation is the same. So if we do the mean minus 2 standard deviations, we'll get negative the mean, which of course we can't have negatives here, so we'll say 0. And if we have the mean plus 2 standard deviations, that's the mean plus twice the mean, that's going to be 3 times the mean. So there's really no work to be done here. You just got to remember in the exponential distribution, the range of likely outcomes is from 0 to 3 times the mean. So let's look at the lifespan of goldfish, right? Let's say the lifespan of goldfish is 5 days. It's not, just making that up. So 5 is the mean. The standard deviation would also be 5, which means the range of likely outcomes is from 2 standard deviations below, which we'll just round off to 0, up to 2 standard deviations in that direction, 15. So 0 to 15 would be our range of likely outcomes. Very, very simple. Now, calculating the probability that you're above or below or between some numbers here is going to be a little more complicated. We'll get to that next time.